Hello, students. Paul Austin here. We're doing the Computer Science Foundation's vector and bitmaps. Now we're on to part 3. We're going to look more at that processing per pixels. As an example of, let's go down here. Yes, an example of what happens in nested loops. Again, a pattern of what happens when you're doing matrix processing, which is what's at the core of graphical processing units, or GPUs. So let's look at the code we had. There we are, back where we last left it off. We're doing a Cartesian plot with size 200, which means we're going from minus 200 up to 200 on the X and the Y axis. Now, last we left it, we had the test pixel function, and this returned true or false. And down inside of our nested loop where we're doing, let me turn that guy off, we do 4x from minus 200 up until 200 by adding that plus 1, so we don't stop at the 199. And that is going to take us from the x-axis like that, and for the y-axis, we're going down the negative space up to the top. Now here we're doing if text pixel, if test pixel. So when this is true, we'll draw the pixel. But what if we want to do processing for every pixel? Instead of it being a logical value, what we'll just do is return the color. That way, this test pixel function can always return a value. Well, instead of true or false, it will always return a value, but the value will now be a color. So let's go ahead and just change this up. When we can get rid of this condition loop, getting rid of conditions, well, it won't make this code particularly faster. But when a machine doesn't have to stop and choose what way to do it, it does allow it to run faster. This is a lower level hardware. Right now, we're using this Python program just to demonstrate these concepts. So we're not going to see a speed change here, but this is what happens at low level hardware. So instead of doing passing a specific color here, what we'll do is we'll turn around and come up with a function, call it pixel color, and we'll still pass in the X and the Y. All right, so pixel color, and we'll change this guy to pixel color. I guess I could have left that function there, but we'll clear it out. We'll just kind of rewrite the function. I'm going to pick, let's see, oh yeah, we'll start off with this one here. Do that radius, and we can say if radius less than 50, keep it something simpler. Okay, going back to that return model, so we could go ahead and return red if it's less than 50, so it means it's closer to the center. Else return color. Here we go. How about the red and blue? Those are our school colors. 0, 0, or RGB 1. There we go. Okay. So I got the if radius, else this, radius is that. We're still using that function here. But now instead of returning the Boolean and having a test logic inside this function, we're just going to turn around and call it. Let's go ahead and run that code in here. Do we get it right? Oh, there we go. It's smaller. We did minus 50 instead of size. So what if we did that size here? All right. Okay, there's our full size. Red outside, blue inside. Now, this point, we're still doing a Boolean test, which is just inside the pixel color. The next step that we want to look at is actually calculating not just like a binary condition, but actually calculating a color. So let's draw upon some of the functions we used last month using the sine and cosine. So let's go ahead and pick out, won't use the radius any longer. Let's get rid of that code here. I'm going to get a color, I'll just do it C. And I'm going to say math, not sine. This is sort of the area of image processing. We take sine and we'll take X times Y. I want this picture, I want the pixels to be a function of both how far away they are from the x-axis and how far it is in the y-axis. So X times Y, of course, this number is going to be pretty large at this point. So I think I'll divide it down by 150. And that's going to be a value. Now, if we want to turn this into, if we want to turn it into a number that's going to be one of the colors, we need a number that's between 0 and 1. If you remember that. I have a piece of code I was going to copy right from over here. Yes, that's right. We're going to take that number. Okay. Let's look at a glance at that. Okay. Remember, sine is -1 to 1. So to turn that into the 0 to 1, what we're going to do is divide it by 2. And then once that's all done, that would give us ultimately, math is cumulative here, of course, the multiplication and division is. That would give us minus 0.5 to 5, so we'll just turn around and add 0.5 to that. All right, that's good. And now, instead of that conditional logic, let's go ahead and we'll just have a simple return. And we'll go ahead, instead of doing a constant color, we're now actually calculating a color. Let me run that in on here. Oh, let's see. I think I got something wrong on that guy. Nothing like typing it live. Okay, yes, duh, that's right. This is the part I wanted to divide by 150. Some of you probably already saw that. So this is this value we're taking the function of. So we're doing the x and y, and then we're dividing that by 2. It's there. Okay. Then drive. Okay, there we go. So now we see that every pixel is both a function of its x location, x displacement, and the y displacement. So instead of, we could be seeing circles, but now we're getting patterns that are much richer. And depending upon the value I put in here, if I say 50, you'll see it's sort of like zooming out. We're getting deeper patterns. I'm almost beginning to see a little bit of checkerboard in there. You can see that some seem to be majority red, some majority black. As we're looking at that, now that we're calculating images pixel by pixel or doing processing it, that's the domain called image processing. It's a subcategory of digital signal processing. It's what goes on in your cameras. We could look at the next step of doing things like taking a picture and making the edges softer or making them sharper. Those are the kind of math operations that happen in that space. Anyhow, that's it for this section. Go code. You are called to create. Amen. Blessings to you all.